In this video, I'm going to look at a Python program, and it's going to read a JSON file off the internet. And then there'll be some of the information in that JSON file will be some data. It's on planets, and it's going to take two of the values, two of the fields in that, the distances from the sun and the average orbital speed of those planets, and then make a plot of sort of velocity versus distance, and finally fit that data to a power law. Okay, so if you want this code, it's just this file. There it is at that URL. Okay, so what are we going to import? At the end, I'm going to also save the plot I make to, I think, a PDF. And so I want to have some control over my file system. So I'm bringing in the OS module. I am going to use matplotlib to do the plotting. I'm going to use numpy to do the fitting. The data that's coming in will be in a JSON format, and it's coming from the internet. So that's those last two imports. The urllib is for getting something off the internet, and the JSON library for interpreting what is brought in as a JSON file. And the JSON in particular, it's on my website, but I actually just found it somewhere on the internet and then placed a copy of it on my website. So let me show that to you. So here is the JSON in question. It starts off with a square bracket, so it's going to, when we read it in, it's going to be in Python a list, and it's going to be then a list of dictionaries. So here's a dictionary for information about Mercury and then Venus. And then one last thing that we're going to have to deal with, that whoever made this file included a in the last position, the sun, which is not a planet. So that would throw off what I want to do. So I'm going to have to sort of eliminate that and then just pull out, I'll be interested to hear in the velocities and the distances, and here they're strings, so I'm going to have to cast them. I think I cast them as integers, though float might have been just as good, maybe better. Okay, so that's what the data file looks like. And here is the code 20 to 22 to read it and bring it in as JSON to turn it into to the format, which is then a list of dictionaries, as we said. Okay, so this 2021 is sort of to get around any like security measures that might be in place for reading data off the internet, any sort of moving across different websites. So it's working, at least for me, but those security things sort of change, and so this would be a culprit if something suddenly stops working. If the security goes up between now and whenever you view this. Okay. Then, as I told you, that in the what they're calling the 9th position, but in terms of lists, the item with the dictionary with an index of 8, since we're going to be 0 based, needs to go. And so here is me sort of, popping off, getting rid of the sun so that all the data is about the planets. I wouldn't mind if Pluto were in here. Scientists sort of got rid of it for some reason, but I had no issues with Pluto. But I do have issues with the sun being in a planet file. Okay. Here is, I need to extract from that data. Let's look at it one more time. I have this list of dictionaries, and then I want to pull out, I want simpler list. I want a list of velocities. I want a list of distances. So I'm doing a list comprehension, sort of. Okay, so let's pull out here. I am looking for D is going to be, D is defined here, where D are the things in the planet_info. So planet_info was a list. D is an element of that list. And then from that element, all I really want is the value which has the name velocity. So it's key value pair. So I want the value for the key of velocity, and then I want it cast as an integer. So that's a lot in one line. Back in my, the way my brain tends to work, being old, I'd probably think of this as, well, there is a for loop here, but I probably like more explicitly go through a for loop and create, append things to these velocities and distances. But that functionality is sort of built in and can be sort of reduced to sort of one line, or since I want two of them, two lines. Okay. But so again, I'm going through the items in the planet_info list. Those are the Ds, and then I want the from AD, I want the value that has a key of velocity, that's D square bracket quote velocity, and then I'm casting it as an int, so parentheses around that. Same thing for distances, and again, that there's no reason that those numbers, you expect those numbers to be integers, except the numbers were large enough that to the significant digits that they had, they were indeed integers. Okay. And I had at one stage printed them out and make sure I had it in the form I wanted. And now I'm ready to graph. So I'm setting up. I get the axes so I can sort of do a little coloring of the background. It's all the values are high, the RGB are high, but the G is the highest, so it's a little bit of a light green. I'm putting in a grid, and I am using PLT, which is from the matplotlib, and I am making a scatter plot, which is just the dots. So let me finally run this. And there's the 1, 2, 3, 4, 5, 6, 7, 8 planets, Mercury, Venus, Earth, Mars, etc. Okay. Oops, I didn't want it that big. I wanted it to minimize. Okay, so I'm plotting on the x-axis the distances, on the y-axis the velocities. This is the size of those dots. This is are they opaque or translucent, somewhere in between. This is a sort of a orangey color of the dots. The edge is a little bit darker. Not that it matters that much. Okay. Now I'm going to move over to fitting. So I'm going to use the numpy module, specifically within it polynomial, and specifically within that fit. And I'm doing a log. Okay, so I'm not going to plot it as a log. That's a different thing. But in the fitting, I'm using log. Let's explain why here in this little PowerPoint. Okay, so I have a form I want to fit to a form of a power law, y equals a x raised to some power b. And so I can take a logarithm of both sides and they still be equal. So log of y equals log of a x raised to the b. If I have a product, multiply two things, then I have a log of them, then it's equivalent to the log of the sum. So a times x raised to the b, log of a times x raised to the b is log of a plus log of x raised to the b. And then finally, when you have a power x log of x raised to the b, then you end up multiplying in with logarithms by the power. So that's the same as b log of x. So now we see that if we use log of y and log of x as variables, then in those variables, this form is linear. And so then the b, the power, it will be the slope. So if I fit with taking the log of the x's and the log of the y's, when I get a slope b, that will be my power. And log of a will be the intercept will be related to my coefficient. And so if the intercept is log of a, then I take the exponential of both sides, and the exponential of the intercept is equal to the exponential of the log of a, and then that gives me a. So if I take the intercept and I take the exponential function of what I find is the intercept in my fit, that will give me my coefficient a. Okay, so that's why I'm doing this. So np is the numpy polynomial.Polynomial.fit, and then I have distances and velocities are lists. I want to apply the math of taking a logarithm to all the elements in my list, and numpy has that ability. So np.log distances, comma, np.log velocities. The degree 1 means I'm doing a general polynomial, can do higher powers, but I'm only going to the first power. So there's going to be a constant and a linear term. So I'll say constant or intercept sort of interchangeably. And then here, the domain, I found that this polynomial fit does some weird scaling things, but not if I say domain equals open close square bracket. Here I am taking the exponent, the fit 0 is the intercept, and if I take the exponential of it, that gave me the coefficient of my power. And if I take the difference between the fit 1 and the fit 0, that gets me the slope, which we found out was the power. And I just printed them out. So there you see them here in my printout. The coefficient was 400. The power was a negative, probably a negative 1/2 if all my numbers were right. With a bit of rounding, the power's a little bit off. Okay, and this is related to Kepler's law, but Kepler's law is typically about the distance in the period, which is related to the orbital velocity that we're doing now. Okay. Now I have my fit, and I would like to add it to my plot. So I'm going to make a sequence of x's from the minimum distance to the maximum distance, and I'm having 100 points. And then I'm going to make a plot of that sequence for my x's, and the coefficient times those numbers raised to the power. 2 asterisks raises it to a power in Python. And so I'm making a plot of my fit, and it is red, but fairly sort of like half transparent. And it's the line width is 1, so it's a pretty thin red line. That line is what I just showed you how to make. I want to display the fit equation on my graph. So I'm saying y equals some number, x raised to some other number, and then in there I'm inserting the coefficient and the power. And I'm placing that on my plot at 2030. So here's my x of 2000, here's my y of 30, there's my equation. I titled the graph planetary data. I had an x label for distance, a y label for velocity with some units. Here is me saving it to a PDF, so me doing my operating system stuff, so that when I save the file just with the file name, it will place it in the same place as where my y is, and then this plt.show at the end is raising this sort of little modular pop-up with the graph in question. So that's what I wanted to show you. So there was some fun. Here's reading from JSON off of the internet, sort of getting around some basic security. Here is using list comprehension to extract. Oh, here was me popping out one of the elements that I didn't want from my list. Here was me from the elements I do want, just pulling out the two lists, the list of velocities, the list of distances that I did want. Some basic plotting that I've done in some other videos. Then here was specific the information to the log to use a linear plot to get a power law plot, and then plotting that power law and the fit equation on the graph and what have you. Okay, that's what I wanted to show you in this one. Thanks for your attention.